For today's notes, you will need in class 66. We are dealing with part 3 of standard 15, which focuses on finding surface area. Today we will be dealing with what is called a right cone. So as a review from our previous lesson, surface area is the total area of all surfaces of a geometric solid. Specifically, when we're dealing with cones, the formula that we use for surface area is pi RL plus r squared. Pi RL calculates the surface area for the slanted part of the cone, and then pi r squared is for the circular base of the cone. Thinking about r, that's going to represent the radius of the base of the geometric solid. L is going to be the slant height, similar to what it was with pyramids. That describes the distance between the apex and the base edge. And then capital H, which is not in our formula today for surface area, but will be important to use to help us find parts of our formula, is the actual height of the cone. That actual height is connecting the apex and the center of the base, just like it did in pyramids. Okay. Testing our understanding of that terminology, we are going to shade the face that should be used as the base. So I'm going to continue to use yellow for that. And then we're going to highlight or draw in a distance that represents the radius. That's going to be the R part of the formula. And then we're going to have another distance that represents the slant height. That's going to be the L part of the formula. So when we're looking at a cone, the circle is the base of the shape, regardless of where that circle is located. So it might be the bottom, it might be the side. If we flipped it upside down like an ice cream cone, then it would look like the top of that solid. The radius is found in that circle, starting at the center and traveling out to an edge. So it can go in any direction, but we usually draw it in either to the farthest point away in the circle, either above or below in this case, or left or right in that case. But we could also draw it kind of like to the front edge, and it would look a lot smaller, but it would still be R. It would still represent the radius. The L, slanted height, starts at the apex and travels to the base edge. So it actually kind of looks like the side of the cone, although that side is not an actual segment in a real cone, but that would be the slanted height. On this one, I'm going to draw it down here at the bottom so it connects to the radius, but it could also be drawn into the top, or it could be drawn in to connect to the edge somewhere else as well. And then just for help visualizing, this distance here, the last side of that little right triangle, would be the capital H height from the apex to the center of the base. So in this triangle, be from the apex down to the center of the base, which gives us the opportunity then to find missing slant heights or to find missing radii by using a right triangle along with our Pythagorean theorem, similar to what we did with pyramids. So that right triangle has a capital H connected to the radius, and then that slant height is the hypotenuse across from the right angle. So we'd have the slant height in the place of the C for C squared, and then our actual height through the middle of the cone, and then that radius would be the A and the B part of that formula. Okay, continuing on, we're going to try to put that into action and see how it goes. Since the goal is surface area of a cone, we're going to start by writing down our formula, pi RL plus pi r squared. Looking for the radius, we know that's going to be connected to the center of the cone. So since 8 is the all the way across distance, the radius will actually be 4. And then the only other thing I need is that slant height, and it looks like they've given that to me over here on the right side of the page. So I'm ready to take all of that information and plug it in. Pi times the radius of 4 times the slant height of 10 plus pi times the radius of 4 squared. The goal for these is to give exact answers. So I'm going to leave pi out of the calculations and just do 4 times 10 for 40 pi, and 4 squared is 16 pi. Since those both include pi, they are considered like terms, which means we can combine them together. 40 plus 16, and then centimeters that are squared will be our units for that surface area. So 56 pi centimeters squared. Moving along to question number 2, we still have a cone, so we're going to continue to use pi radius slant height plus pi radius squared. I'm noticing in this figure I don't have a radius, so the best place to draw a radius in is to connect it to other features that are already given. Right here would be the best place for us to visualize that radius, because then we have a right triangle that we can use to help to track it down. Our right angle happens between that capital H height and the radius. Across from the 90 degree is that slanted height. So if we're using c squared equals a squared plus b squared, 17 will be the c value, and then the a and b values will be 15 and r. 17 squared and 15 squared would be taken care of first. We're going to subtract that 225 over, which leaves 64 behind. And then when we square root, the radius turns out to be 8. I think that gives us everything we need for our formula. So surface area will be pi times our radius of 8 times our slant height of 17 plus pi times our radius of 8 squared. Calculating what we're able to, but keeping it exact, will involve doing 8 times 17, 136 pi, 8 squared, 64 pi. So then when we add 136 and 64 together, we end up with a surface area of 200 pi square inches this time for our label. All right, go ahead and flip the page and meet me over there for a few more examples. All right, continuing on to question number 3. I'm not sure why there's a second cone drawn here, so we're just going to focus on what they've given us. Looks like a cone, so surface area again will be pi radius slant height plus pi radius squared. Again, that radius looks like it's missing, so I'm going to add an r to the picture. But it seems like we are also missing our slant height. So we have 2 things to track down here to try to get us to the point where we know enough to fill in our surface area formula. This 6 is going to be that capital H height, but there's not a place for that in the formula. So with the addition of a little angle clue here of 70 degrees, this seems to me like we're going to need to be in SOHCAHTOA mode. We've got an angle available and a side available. So if we think about that radius first, our 70 degree reference angle is adjacent to that radius side. And then we also know the height, which is actually the opposite side of the triangle. So that means that we're going to be using tangent, it looks like, to help us find that radius. So tangent of 70 will be equal to the opposite, which is 6, over the adjacent, which is r. Multiplying by r and then dividing by tangent 70 is going to give us r equal to 6 divided by the tangent of 70 degrees. Now, if I'm thinking ahead about how to handle this calculation, I know that that's going to create a decimal. That radius, however, needs to be used in multiple places in my surface area formula, so keeping it exact in my calculator is not as easy as with some of our other problems we've done. Since that's the case, and I know I'm going to eventually round to 2 decimal places, I'm just going to leave a lot more than 2 decimal places for right now to minimize rounding error. So instead of calling it 2.18, I'm going to keep going and use 5 decimal places, because if I use that much precision, it shouldn't affect and it shouldn't cause any rounding error later on. Okay, so radius is tracked down. Now we're moving on and we're looking for slant height. So we're not going to use the adjacent anymore, but we can still use the opposite, and then that slanted height would be the hypotenuse. Opposite and hypotenuse send me towards a sine equation this time. Sine of 70 equals 6 over slant height. Again, that variable's in the bottom, so we're going to multiply it over and then divide. So L will be 6 divided by the sine of 70. So we've got 6 divided by sine of 70. And then same thing with this. I could keep that safe and just click the answer button when I need to, but that gets to be a little bit complicated for some of you. So let's just leave 5 decimal places here as well. And then we'll just use these longer decimal values. I guess that would round that up to a 7 as we substitute into our formula to make it a little bit less overwhelming. Okay. If we take everything and we put it where it belongs, we're going to have pi times our radius of 2.18382 times our slanted height of 6.38507. And then we're going to add on to that. I'm going to run out of some space, so I'm going to wrap it around pi radius squared. So 2.18382 squared. Now, because our goal is to round it all to 2 decimal places, we're just going to type it all in one long string. So pi times radius of 2.18382 times slanted height of 6.38507. That's where you could have used your answer button if you wanted to, since that's still on the calculator there. Plus pi times 2.18382 squared, radius squared. Go ahead and click enter, and now we'll officially round it to 2 decimal places, 58.79. So our surface area is approximately 58.79 square meters. So significantly more work there just because both the radius and the slant height were missing. All right, our final task today is to take a look at some composite figures. Part of the surface area standard has us find surface area for figures that are combinations of solids. So when we look at this first composite figure, it looks like we have a small cone and a larger cone. So we're going to find those 2 surface areas individually, and then we'll end up putting them together at the end of the problem to cover the surface area for all of the composite figure. The place where they're touching is just at the very apex of each cone, so that's not actually going to cover up any of the area and send it to be on the inside of the solid. In these other cases, we might end up with some area that gets lost because it ends up on the inside of the solid. So starting with this small cone over here on the left, pi RL plus pi r squared, looks like we've got a radius of 2 and a slanted height of 6. So nothing for us to track down and find, just values for us to plug in for the R and the L in the formula. And then I'm going to keep this exact, even though we're rounding at the end of the problem. We're going to try to avoid that rounding for as long as possible. So that small cone surface area is 16 pi. Looking at the larger cone, same formula, so pi RL plus pi r squared, but a different larger radius and a different larger slanted height. So this time pi gets multiplied by 3 and 9, and then the radius of 3 gets squared, which will give us 20 pi and 9 pi for a total of 36 pi as the surface area of the larger cone. So to finish this out, we're going to take these two surface areas and we're going to add them up to find the total. So that whole composite figure will be 16 pi plus 36 pi. That'll give us a total of 52 pi, which if they wanted an exact answer, we would be done. But since our instructions are to round, we're going to go ahead and type that in, 52 pi. And that gives us our surface area of 163.36 square inches. All right, this next one looks like it's actually going to combine two of our solids from previous days' worth of notes. I'm looking at the bottom of this solid and I'm seeing a prism. So we're going to use P capital H plus 2 capital B for that part of the figure. And then the top is going to be a pyramid. So pyramids, let's come down here a little bit to give ourselves some space, are going to be PL over 2 plus capital B. However, I'm noticing that both of those formulas would include this surface in here. I'm going to highlight it actually. So both the pyramid and the prism formula would include that yellow rectangle, which is actually a square in this case. But that yellow rectangle is no longer a surface in my solid. And so that means I need to get rid of that part of the calculation. So for the pyramid, that's the base. That means that this base can just go away and not be part of the calculation. All that's left is the PL over 2 part. For the prism, that's one of the bases. So that means I could just get rid of this number 2 here, and instead of adding 2 bases, I just have the 1 at the bottom of the solid. Now, there are other ways to handle that, but sometimes it's easiest to just adjust your formulas at the beginning of the problem. Other times it's easier to find your surface areas, add them up, and then subtract away the surfaces that are double counted and not visible anymore on the outside. All right, when it comes to the prism and the pyramid, I feel like the base shape is the same for both. So this is where most of the clues are located about that base. If these two sides are both 8, then the other two sides are both 8 as well. So our perimeter would just be 4 of those 8s put together, or 32. The actual height of the prism, distance between those yellow bases, would be 5. And then for the area of the base, it's a rectangle, technically a square. So we're going to do lowercase b times lowercase h, which is just 8 times 8. We take that and we plug it all in. We've got a perimeter of 32 times a height of 5. And then we're going to add in only the one base that we can still see on the outside of that solid to give us the surface area for the prism part of this composite solid. So go ahead and multiply 32 times 5 and then add in that 64. That gives us 224 for that portion of the problem. Looking at the pyramid, we've got the same perimeter that we can use, so 32, but then we're missing the slanted height. We have a capital H height right here, but we're missing this slant height. So we need to find that with a little bit of help from this triangle inside that pyramid. They're telling us that this dimension is 6, but we really also need to know this one since we don't know any angles. So if you think about that little distance that's traveling into the center, that would be like traveling into the center of the square at the bottom as well, which is actually just going to match the halfway distance across the front of that figure. So that little distance will be 4, since that whole base edge is 8. And I think that means we need to do a little Pythagorean theorem off to the side. The C part will be the L, so L squared will equal 4 squared plus 6 squared. L squared then will be 16 plus 36, and L squared is 52. square root, and if you like, you can simplify that. There's a perfect square factor of 4, so it will become a 2 root 13, but because we're rounding to 2 decimal places at the end anyway, you can get away with just leaving your slant height as the square root of 52. We're going to plug that in here. I'm going to keep that exact for as long as I can, so 32 times 2 and then divided by 2 will give us a 32 root 13 as the surface area part of the pyramid that we can still see. And then like our last problem, we're going to need to combine those together. So the 224 and the 32 root 15 are going to get added together to give us our final answer. 224 plus 32 square root 13. And then that's the point in time when we want to go ahead and round to 2 decimal places. 339.38 square meters for that composite figure surface area. All right, last but not least, this one is a little bit different. This one we have a prism, so that box-like shape where we're going to use P capital H plus 2 capital B. But then we also have a cone. The problem is that the cone is not actually all visible. It's like we're scooping out this shape. So the side part of the cone, we call that the lateral area, is there, but this base is actually an open hole. So if we think about the official formula for a cone that we worked on today, it includes pi RL, but it also includes pi r squared for that circle. But if that circle is open, that part of the formula is not going to be important to include for this particular composite area. In fact, that circle has been covered over as part of our base as well in the prism formula. So we're actually going to need to subtract it away from our final answer so that that can be open and not included as part of this surface area either. So this is actually too much surface area when it comes to the prism because it has that open hole. So I'm going to remind myself that I need to adjust that by subtracting that circle to open up that spot on the top of the prism. Okay, with that being said, we're going to visualize this as the base of the prism, which means when we're looking for P, we're looking for this distance around that outside edge. So it looks to me like that's just going to be 4 sides that are all equal to 6 for the perimeter. We've got a height between the bases of 6 as well. So this prism is actually a cube. And then our base area would be the area of that rectangle or that square, which would just be 6 times 6 or 36. So if we start to plug that in for our prism calculation, we've got our perimeter of 24, our height of the prism as 6, and then 2 of those 36 bases, but that circle needs to get opened up. So we need to remove a circle that has a radius of 2. The 24 and the 6 can be multiplied and added to the 2 times 36 part of this. So these will all combine together to be 216. But this I'm going to leave subtracted off the end so that I can keep that answer exact for as long as possible. Moving over to the cone, that radius of the cone is 2, but it does look like we're missing our slant height again. So right there, that would be our slant height. Our right angle is up top. So we're going to do another quick Pythagorean theorem off to the side, where L is our C, and then our A and our B are equal to 2 and 6. So L squared will be 4 plus 36, which means it's equal to 40. Go ahead and square root both sides, and this is where, since we're going to round eventually, you could just leave it as root 40, or you could simplify it to be 2 root 10. So that slant height joins that formula, and if we're keeping this nice and exact, really all we can do is 4, and then there's a pi and a root 10 that attach onto that. We've got our two surface areas tracked down, making sure that that top part is open. So now we just need to add those two together. Kind of ran out of space to show that, but we're going to take this, and we're going to take this, we're going to add them up, and then that should give us our rounded answer for surface area. So 216 minus the 4 pi for that opening needs to get added onto this 4 pi square root 10. So a total surface area for this composite figure of 243.17 square millimeters. All right, that's it for today. Thanks for learning about cones and also practicing composite figures for a while. We'll see you back in class.